Hello viewers, today I want to discuss on a theorem in algebra. The theorem is that at here K is an algebraic closed field. Let R be a commutative ring and P subset of R a prime ideal so that P is radical, that is P is equal to square root of P. It is a notation, it is radicalization notation. Yes, P is a prime ideal. A, an ideal of a commutative ring is said to be a prime ideal if it satisfies the following condition. There are two conditions. One condition, P always a proper subset of R, and second condition, in any two elements A and B belongs to R such that the product of two elements AB belongs to P, then either A belongs to P or B belongs to P. This is the definition of prime ideal. What is the definition of radical? Radical ideal or ideal which will be a radical such that an element X in the radical if and only if some power of X is in P. Now we want to prove. Let R be a commutative ring, this is provided, and P subset of R be a prime ideal, this is provided, and again radical of P, rad P or square root P are same notations or radicalization notations, is equal to X belongs to R, Xn for some n belongs to positive integer. To show P is a radical, we must prove that Xn belongs to P, that will imply X belongs to P. Let us consider Xn belongs to P imply X belongs to P for n greater or equal to 1, X belongs to R. If X to the power n plus 1 is equal to Xn into X belongs to P, then either Xn belongs to P or X belongs to P. Actually here we have using by the help of the induction theorem. For case of n is equal to 1, this case is obvious to the definitions. And according to our assumption, of these things, assumption it will still have Xn belongs to P and X belongs to P. For the case of Xn plus 1, this line is come from the consideration line. Yes, so radical of P is a subset of P, prime ideal subset. If X belongs to radical of the prime ideal, then Xn belongs to P for some n belongs to the positive integer by the definition of a radical. For every ideal of R, the inclusions or the reverse inclusions P subset of radical P is obvious, so is not necessary to prove. Hence the proof P is equal to radical of P is equal to square root of P P by the two inclusions. One inclusion P subset of radical of P and another is radical of P subset of P. Yes, this is the proof of the theorem. Thank you for watching.